Good evening, guys. So I'm Kavisha. So today tech talk about modern DevOps. So today's speaker is Nilesh Janandana, a software architect at WSO2. So warmly welcome Nilesh to the session. So hands on to you for continuing the session.
Thanks, thanks, Kavisha. I'm gonna share my screen. Right. Can you guys see my screen? Uh, can you see the screen?
Yeah, Nilesh.
Okay. You can see the screen, right?
Yeah,
Okay.
can see.
Thanks. Right. Today I'm gonna be talking about modern DevOps. So I actually had a slide earlier, a different slide, and a couple of fourth year students pointed out to me on Slate that that's the exact same slide that I did for them on their lecture. And when I asked for the target audience from the organizers, Chamod and Sevandi, what they told me was that the target audience would be the people who didn't come for the lecture. But then I thought that, okay, so if you don't come to my lecture, then I'm not going to repeat the lecture again. So I changed the slides. So this is going to be sort of like a different slide deck today that I'm going to be presenting. So the table of contents is what we're going to talk about is we are going to talk about what DevOps is, and we are going to talk about after that the containers and orchestration, CI/CD, testing, monitoring, deployment methods, service mesh, chaos engineering. All of these concepts, I would be covering it as a case study instead of going through the concepts. This would be sort of like a case study, sort of like a presentation. So let's see what the case study is about. Before we get into the case study, I just want to sort of like introduce you to what DevOps is. So basically, the term DevOps, what DevOps came to be before DevOps, what happened was there was in organizations, there was developers, the software engineers, and then there was system administrations or the operating ops sort of like people. So what happens is the software engineers would develop the code, and then they would just give the operations guys to deploy the code. When you say deploy, what it means is that basically you would be serving it up on the internet like Facebook, Google, it's running, and they maintain it, they maintain the issues, they make sure the system is up and running and working properly. So that's what ops guys do, and the developers are the ones who do the bug fixes, patch changes, develop new features, etc. So there were some problems here. It's like this. So the developers would be like, if it worked fine in your development environment or your local computer, they'd be like, okay, it's operations problem now, it's not our problem, you go and fix it, that's not my problem, I'm going to sleep. So that's the attitude engineers have, right? So there was this uh, a lot of rift between developers and ops people because of this. So as a solution, I think IBM was the one who did this first. So they brought in developers and the operations guys together and then put them in one room. And then we call it as, you know, um, DevOps. And after that, they collaborated. So the developers know how the operations worked, and the ops guys also knew how the code was written, what were the changes of the code, and stuff related to the code, like if something happens, that they had an understanding of how the system should be running. So there was no disparity anymore. It was, everybody was working together, and it was much better. So what is DevOps now? When you look at it today, if, since all of you are students, most of you, and from the IT industry, you know that DevOps is sort of like a hyped up topic. So everybody is looking for DevOps. DevOps engineers are in high demand, and people are looking for DevOps engineers of 10, 15 experience and etc. So what the hell is DevOps actually? So DevOps is basically a combination of culture, practices, and tools. That's it. DevOps is sort of like a mindset. So you don't have to specifically be a DevOps engineer to do this. Like engineers, operations guys, everybody should have this sort of like DevOps mindset. So the mindset is there's a culture in DevOps, there are a set of practices in DevOps, processes, and to implement those practices or processes, there's a bunch of tools. So all three together is what we call DevOps. And a DevOps engineer should be able to understand these three topics, know what they do, and should be able to sort of like implement this organization wide, like set the mindset up organization wide, uh, among developers, QA engineers, and all of these things, like how all of this works. So a DevOps engineer to me implements these things and also like sort of like spreads awareness to others. So let's look at the three culture tools, processes, and tools. So when you look at culture, it's basically like sharing the feedback, the best practices, the knowledge, and how things are working out. I mean, you can be critical and you don't take things personally. There's always like you have to be humble, you have to listen to what others say. And the mindset of DevOps basically, like everything needs to sort of like be process automated and all of these things. So that's sort of like the culture everybody should have, like have security relate, like when you're developing you have to do put security first. You have to think about when you're developing, like your software is not going to be running on your own laptop but it's going to be running on a server. You think about those stuff. So all of these things are cultural. So this is the mindset that you have to develop as an engineer or as a DevOps engineer, etc. This is the mindset the organization as a whole should develop. The next thing is the practices. So the processes in DevOps. So there's a famous quote saying, automate yourself out of a job. So basically, you automate everything. There's no manual work. Everything you do, you automate it. Like there are concepts like infrastructure as code. There are concepts like CI/CD. There are concepts like release management, rollbacks, observability, alerts, GitOps. There are so many processes and practices in DevOps that you need, as a DevOps engineer, you need to be aware of, and then you need to sort of like introduce to your company, to your project according to your needs. And then finally the tools. So a lot of people that I know, like they take an AWS certificate or they do a Google cert, Kubernetes cert, and they say that they are DevOps engineers. They're not. Just because you know one tool doesn't mean you are a DevOps engineer. You need to, and like anybody can learn any tool. That's all right. Like, anybody can learn it, right? So it's the mindset that matters. So the two things, the processes and the culture, those are the two main things, and the tools come afterwards. So if you know which tool to use in which in a given situation, learning the tool and then implementing is not a big deal. So of course, certain tools like Kubernetes, Docker, and all of these things, you need prior experience, and you need to. It's good to have a certificate, etc. But still, tools doesn't define who you are as a DevOps guy. If you know the processes, if you know the concepts, if you know the culture, learning a tool is not a big deal. Okay. Right. So then there's one last thing called CALMS framework that I wanted to touch upon. So this is the most popular framework for DevOps. Basically, it says culture, everything that I spoke earlier, culture, automation, lean, these are agile practices. Then you measure as in how many deployments you do for a day. Dora metrics. There are a few metrics like that. How many releases you do, and then sharing. You share your feedback. You go back and you fix things. You fix the processes. You continuously try to improve your processes, your automations, etc. So this is what, in a nutshell, what CALMS is all about. Google it and learn more about it. Okay. Right. um right, so from here on, what I'm going to do is I'm going to be touching a case study. So modern DevOps, let's look at what the case study is. The case study is running the election system in Google Cloud. So you know that there was an election system that was done in Sri Lanka 2019 presidential and etc. So this is an open source solution, a system. So the software architecture and how things were run in presidential election 2019, you can look at Dr. Sanjeeva's blog, which was referred here. And then the requirement doc for that particular election system is also there. And also the entire system is open source, which means all the repositories and everything is in GitHub. So the repository link is also there. So what I'm going to be discussing today is not how we actually implemented DevOps in this election system, but rather if I were to implement it in Google Cloud, how I would implement it. Okay. It's not how we implement it. It's not the original implementation. We are just going to go through a case study of how if we are going to implement it in Google, how we are going to do that. Right. So yeah, it might differ from the actual implementation that we did. I just want to clarify that here. Okay. So let's look at the software architecture. This particular election system has about, I mean, there's a bunch of stuff here. You don't have to worry about much. It has about 10 to 15 microservices, the entire election system, and they are communicating through HTTP REST based protocol communication, and they are having a MySQL database, and then they have this identity and access management, sort of like RBAC we call it. Don't have to worry about it. And then the typical requirements, like system should be scalable, system, because it's an election system, security, it has to be a security first approach, and this has to be highly available, and it should obviously support disaster recovery. In case of a disaster, a 15-minute downtime is acceptable. I mean, these are not the original specs of the how we implemented it. I'm just giving a case study, a hypothetical case study. Okay. And so I spoke about microservices. So what the hell is microservices? So microservices is basically, rather than building one big software altogether, you break it into small services called microservices. So the election system, in this diagram, we can see a few components like the nominations, counting, etc. There are third party results, all of these things. So these are different microservices. Rather than put them all into one big software, we put it into several smaller microservices to run. That's what microservice architecture is. So let's look at the key decisions or the processes that we define, that we are going to define on this election system that we are going to run on Google Cloud. So we are going to say microservices will be run in a containerized environment. I'll get to what containerized environment is. And then we also decide that because it's going to be containerized, we are going to say Kubernetes will be used to orchestrate this, right? And we are going to have three environments set up called development environment, which is used for developers to test things out and do development. And then we are going to have another environment called a staging environment, which is used to sort of like test things out, like how it would actually work in production. That's where we do this testing on that environment, staging environment. And then finally, the production environment, which is the actual system where it's running and everything is working properly, right? And then again, security first approach always, because given the sensitivity of a project like this, security should always come in first. And another thing is the whole DevOps culture I was talking about. Everything needs to be automated via tools or scripted or whatever. There would be no manual work. And GitOps as a concept, we will be using it. I'll explain what GitOps is later. And then for the deployment pattern, so now because this is an election system, this is not going to be running every day, right? It's going to be running only on the day of the election, which means when we do updates to the system, it's going to be patch updates. It's not going to be breaking changes. It's just bug fixes. So stuff like that rolling updates is the ideal deployment pattern for a scenario like that. So that's why we are going with rolling updates for the election system. Okay, so these are the key decisions or process definitions. And like at any point on this case study, if you have any questions, just ask, and I believe Kavish or someone would voice it out and I can answer it then and there. Okay, right. um right, so what the hell are containers and orchestration? I already told in the previous slide here that microservices will be run in a containerized environment and Kubernetes will be used to orchestrate. So what the hell is this? So why does software break in production? So it's mostly because when developers do their develop the application on their local machines, it's at the end of the day all of us develop in our local machines, right? Then only we ship it to the servers to run it in production. So there's always our local environment and the server environment are always different. So there could be gaps between our environment and the server environment. So by using something like containers, it allows us to sort of like, the first thing, make sure that the software that runs on our machine will be running exactly like that when we run it uh, in the server as well. So it gives us portability. And the other things is that the things we mentioned, like scaling, rollbacks, immutability. So there are a lot of advantages that come to us when we use containers. So in a microservice situation, if we were not to use containers, then we would have to sort of like spin up servers per microservice, which is going to be expensive, and to be honest, frankly, it's going to be time consuming, and have to set a lot of things up. But rather, with this approach, with the container approach, all of our applications would be bundled as a image or a container, and then run as a container. And then we can scale these containers individually to handle like for example, say 1 minute you are getting 5,000 or 10,000 requests per second. So this particular microservice can scale independently from others and support that kind of a load. So so these are the things that would that sort of like give, that's why we go with containers here. And then so right, so we chose containers because it allows us to sort of like have the portable environment, and it sort of like allows us to do scaling, and makes things easier for us and all of it. All good. But managing these containers, like let's say that you have 10 microservices, and each of these microservices is scaled to 5. Altogether, now we have 50 containers running that we need to manage. So a person or a couple of DevOps engineers manually managing these containers would be a nightmare. It's going to be hard. So rather than that, there's this concept called container orchestration, which means there is a tool like Kubernetes or something else that we can tell them, like, manage these containers for me. I don't want to manage it, you manage it, and if there's something wrong, just let me know, I'll fix it. Right, something like that. So that's what happens. um, so in an orchestration, what happens is that we would sort of like give a bunch of resources to the orchestrator, like say Kubernetes. They are going to say, all right, so these are the virtual machines you have. And I'm going to say, hey, Kubernetes, run my Java application. And if there are about 10,000 requests per second, scale it up to 5 instances. If not, scale it down to 2 instances or whatever. So stuff like that, I can just tell Kubernetes, and it would automatically do the needful behind the scenes. I don't have to worry about it, just magically happens. Okay, so that's what orchestration is in a nutshell. And Kubernetes is the default choice today for orchestration. I'm not going to talk about the others. So yeah, for this particular project, now we have chosen containers to sort of like bundle apps together, and then we have chosen Kubernetes to run and scale our application on demand. Okay, right. All of that is done. So these are just key decisions that we made. The next step is planning. The first thing is we need to plan the infrastructure for this election system. So just don't worry about the diagram much. It's not a big deal. I'll just go through it. So we have a firewall. and we are allowing 443 only. 443 is the HTTPS port, so you are only allowing 443 incoming traffic. And then we have a load balancer. So the traffic hits the load balancer, and the load balancer forwards the traffic into a private Kubernetes cluster. Note the word private here, because again, because of the security first approach, we don't expose Kubernetes publicly. Everything will be private. So the traffic will be, forwarded into the private Kubernetes cluster, and then whatever the APIs that are running here would, serve the traffic and, give the responses that are needed. And then again, in a different private subnet, we have a MySQL running, because remember we talked about, we said this particular project needs a relational database. So in a different subnet, a Google managed MySQL will be running, and this will also be highly available in availability zones. And we would want to do stuff in the Kubernetes, right? We want to talk to Kubernetes API, and we want to tell Kubernetes, hey Kubernetes, run my nominations app. Hey Kubernetes, scale my application. So we need to give Kubernetes such instructions. And because Kubernetes is private now, we cannot directly from our computer, we can't go and directly tell Kubernetes to do something. So for that, there's this thing called Bastion host, which is in a public subnet. So me being a user, I authorize against Google IAM, Google Identity and Access Management System, and then via, there's this thing called Google Identity Web Proxy. Don't worry about it. So via that, I can access this Bastion host. This is a VM. I can access this VM, and via this VM, I can, send commands or instructions to the Kubernetes cluster to do stuff, right? And other than that, these are sort of like Google services that we would use. Because of the security first approach, we are going to use like Google Secret Manager to store sensitive information. And then we are going to use Google Cloud Build to do continuous integration and continuous deployment, pipelines, CI/CD pipelines. And then we are going to use Google Stackdriver solution to do our observability monitoring and alerts and all of these things. And our applications, I told you, we are now bundling them as Docker images, containers. So these needs to be pushed somewhere secure in order for us to, run them in this Kubernetes cluster. So we would be using Google Container Registry for that. Just a simple implementation, not a big deal. Okay. So this is how we plan the infrastructure. So this is usually done in the company by somebody who has, a Google Cloud Architect certificate, or somebody who knows Google, somebody like that. They would be the ones who would be, deciding this particular architecture and the network. Okay. And then you would define the environments, right? So I'm going to have, for this particular project, as we described, we are going to have three environments: a development environment, a staging environment, and a production environment. So in the development environment, it's a quick setup, because when we start the project, the developers, who are developing these microservices, they need to get started quickly. They need to, work together, collaborate, and do things. So we quickly set things up in the development environment, and then we evolve the architecture as we move forward in the development environment to sort of like match what we need when, the project comes into a mature stage, right? So that's the development environment. So once it hits a sort of like a mature stage in the project, where, now you are ready to sort of like test end to end, to see how things are working out, you're ready to showcase it to somebody else external to the organization, that's where the staging environment comes in. So then we set up the staging environment now. And staging environment, of course, we are going to do security first approach, and this will also be an evolving architecture, because now we are hardening security in the staging environment. And because of that, there could be, issues like firewall ports needs to be open, certain things we discover at the staging environment level. So this will be an evolving architecture, mostly in security related. And finally, the staging environment needs to be as close as possible to the production environment, because that's how it should be, because whatever we test in the staging environment, goes into the production environment, and after that it's live, you can't test it anymore. So staging environment definitely need to be close as possible to the production environment. In this situation, staging environment and the production environment would be equal, right? 100% everything would be equal. And in the production environment, of course, to be set up, at the end, once the staging environment is also stable, we start setting up the production environment, security hardened. Everything we learned from the staging environment, and the architecture evolved on the security, all of those things apply to the production environment. And we make sure that it's close as possible to how staging environment is configured. Okay, so these are the environment definitions. So when developers do releases, or push their application, it's do changes to the application, it goes first into the development environment, and you check things out, you test. If it works, you push it to the staging environment, you test again, now with the thing, imagining it's close to being production, and then you test again, and if everything works out, you push it to production, and you're good to go. And if something goes wrong, you can always roll back as well. Okay. And right, so now we planned our infrastructure, we planned our environments. The second step is setting up our development in environment infrastructure. So now there's this thing called infrastructure as code. So we have to select an infrastructure as so we select the process as infrastructure as code. There are two ways you can set up this environment up. One thing is, you can log into Google Cloud and you can press the couple of buttons, create these VPCs, and do all of these things by pressing the buttons. But that's not really a good approach. Um, in the DevOps uh, way, what we would do is, we would do infrastructure as code. Like, we would automate these things, we would have immutable code for these stuff, so that it's easier for us. So that, for example, let's say that I set up the development environment as code. I configure all of it as code, then it's easier for me to set up the staging environment as well, because the code is already there for the development, for setting up this entire architecture. Um, and also, like, this is an election system, which means that it's not going to be running every day. So once the election is done, we would destroy everything, and then we would start again when the next election comes. So which means that when we have a code like that, well, if our entire setup infrastructure is set up as code, we can very easily use that code and then respin the environments as and when needed. And then you have to select a tool to sort of like do infrastructure as code. There are few tools out there: Terraform, Pulumi, Crossplane, Chef, Puppet does a lot. So we are using Terraform for this particular one, because now Terraform is actually becoming sort of like an industry standard, and everybody knows Terraform, and it's easier to use. For this particular use case, Terraform seems to be the best choice out of the lot that I said. Step 3 is, we are going to set up a CI/CD pipeline. Um, so here, what would happen is, we are gonna push or commit our code, and then in the CI pipeline, we are going to build it, we are going to do some testing, we are going to unit test, we are going to integration tests, and then we are going to review it. We are going to then push it to staging, and then from staging, we are going to push it to production. So this is the continuous integration and continuous deployment pipeline that we are going to have. For this particular one, how this trigger would happen is, basically, we are planning to do like, in Git, there are branches. So the main branch, or the master branch, would be the stable branch. So whenever you do a commit to master, uh, you know the software will get built, and then get unit tested, get integration tested, and gets deployed. Okay, and then we can promote it to higher level environments such as staging and production. Okay. um right, so advantages of CI/CD, as I said, can do rapid releases. Like, you see how Netflix is changing every day, that's because of CI/CD. uh, Zero downtime, like Facebook pushing features every day without any downtime. All of this is thankful for CI/CD and a concept called zero downtime. um, so CI/CD allows us to do rapid releases, and allows us to sort of like do reduce costing, and gives us faster feedback. So, like, some organizations, they don't have CI/CD practices. What they would do is, just a developer would SSH or something into the server, they would build it manually, and then do deployments and do all of these things manually rather than automate it. And then there could be problems, there could be going up and down on something's wrong, the QA engineer saying there's something wrong and all of these things. So CI/CD actually makes a lot of things faster and easier, just a quick setup, and then everything is just smooth sailing. Then CI/CD tools. So there are a lot of CI/CD tools. The election system itself, as the link was there, it was in GitHub. So for this one, we can use GitHub Actions, but we are going to use Google Cloud Build because, again, because of the security first approach. This is open source and GitHub Actions are there, and the particular project, if you're going to have some sensitive information like secrets or something in GitHub Actions, there's a chance it's available to the public. Therefore it's better to run it in Google Cloud, which is 100% private. So we would, you know the repositories will be there in GitHub, but the pipelines would run in Google Cloud Build, and only the people who are authorized inside Google Cloud Build can actually look at the build logs, what errors were thrown, and all of these things would be in Google Cloud Build. So other than that, there's a bunch of tools that industry is using. You can check it out later. Um, right, step 4. We have set up our CI/CD pipeline. We have set up our infrastructure on dev environment. Now in the CI/CD pipeline, I mentioned tests. So there are a few tests that we can do in this particular system. First one is unit tests, and this is the responsibility of developers. So developers needs to write unit tests on their code. So what we can do as DevOps engineers is, make sure these unit tests are run and tested when it gets built, right? So that's what the role of a DevOps engineer would be in that case. And then there's another one called code quality tests. So typically, there are few tools. Can't remember the other names, but SonarQube seems to be the most famous one. So what happens is, like, you can test the quality of your code. Like SonarQube would definitely do and check if your code is, whether your code is good, whether it's quality, whether it has any vulnerabilities, whether it has any credential information or secrets that you have accidentally committed. It does all of these things for you, and it gives you feedback on, like, whether to fix, what needs to be fixed, and etc. And then we can set up a rule here saying that, okay, so if your code is bad, like if it doesn't, there are things called quality gates in SonarQube. So if it doesn't pass the default quality gates, the CI pipeline should stop from there, and then the code shouldn't get built, and then the developer should get feedback, and developer should fix these things before the code can actually get built and deployed into the dev, prod, and staging environments. Then we do vulnerability scanning. Again, when we do uh, these are called supply chain security and etc. So vulnerability scanning is very important, because if these vulnerabilities can be exploited, and then your system can be attacked from the inside, and your entire system can get screwed up. So we do vulnerability scanning. For this particular one, we have chosen Trivi to do vulnerability scanning. um, Trivi is basically a lightweight Docker image vulnerability scanning tool, which sort of like goes through everything and tells you whether there are any vulnerabilities in your Docker image. And then runtime scanning. Runtime scanning is when your container is actually running. So sometimes there could be, like, for example, if you are using Node.js, and then if you are using some npm module uh, developed by a third party open source somebody, right? I mean, you don't know what the code is, right? You just use it. They can be running a process to sort of like mine Bitcoin or something like that behind the scenes in your server. We don't know. So there are a lot of things like that. So and vulnerability scanning doesn't really expose everything. So you have to do runtime scanning, like, and make sure that the system is supposed to only do what it's supposed to do. So there are few ways you can do it. Sysdig is the popular one. The open source one is, and you have to pay for it. And Falco is the open source one, and there are a few others in Linux kernel itself called AppArmor, and another one called I can't remember. Um, yeah, and then that's what we would be using for this particular system. And integration tests. So I mean, there are so many integration tests, test suites there are, um, for JavaScript, etc. So there are, Mocha and few others that allows you to do integration tests. But for this one, we are going to go with functional tests because this is a UI based system, and the end-to-end UI, at the end of the day, the UI should never break, and the UI functionality should never break with the rest calls and all of it. So we're going to go with Selenium tests, scripted Selenium tests on the user flows for this particular system to make sure everything is working. And we are also going to do load tests via a tool called JMeter, because we know in the election we have this information, right? We know how much of a load the system is going to get at peak time. We know these things, so we can maybe double it or make it 150% the maximum value, and we can run JMeter and see if our system is handling it well, and it works. Okay, and then after deployment, UAT tests, these are manual. These would be done by external parties like the election commission or somebody else, and make sure that everything is working. Those are just process tests. Um, Step 5. All right. So now we have set up our environment. We have set up our CI/CD pipeline. We have set up our testing. So our software gets built, and our software now got deployed. And now we need to observe how our software is working or running in our development environment and the higher environments. The first thing we need to check out is how CPU, memory, storage, and network, all of these are working in our running system. So Stackdriver in Google, Stackdriver is the default one. Or you can go with there are other tools as well, but let's stick with Stackdriver, which is what Google has. And then logs. So you have to observe logs, like your system would be printing logs on issues, uh, stuff that are happening. If your system crashes, you need to look at crash logs. So all of these needs to be persisted so that you can sort of like analyze later, and you can see if there are errors, how many errors there are, and all of these things. So that's, again, we can use Stackdriver for that in Google. Runtime security I already explained, and we are going to use Sysdig for that. Crash loops. If the application is crashing, we need to know that. So you can use Stackdriver to that as well. Latency and tracing. So for example, let's say that you have three microservices to sort of like complete one request from front end, like service A talks to service B talks to service C, and then service C returns the response. So if this entire request, service A to B to C, the full request takes about, say, 500 milliseconds or 1 minute to complete, right? Then there's a problem. That's called latency. So we measure the latency. So we would have non-functional requirements like, okay, every request in this system should be served under 200 milliseconds. It cannot be more than that. That would be a non-functional requirement. And then to measure it, we need to measure latency. Now with latency, we can figure out, all right, so whether this system meets our non-functional requirements or not. The next thing we need to do is we need to debug it. Now we need to say what happens in this request. So it goes from service A to service B to service C. Where does it go wrong? Why is it slow? That is called tracing. So at tracing, we can see, all right, so the request come to service A. It takes 2 milliseconds to go from service A to service B, and service B to service C, it's taking about 500 milliseconds. So the problem now is from the call that goes from service B to service C. So we pinpoint that, and we identify that, okay, this is the place there's the problem with, and then we can sort of like debug and see what's going on. And then I told you containers, Kubernetes, they manage the state, they manage health checks and make sure all of this is working. But still, to manage our uptimes, manage our SLAs, we need to have external health checks as well. So we can use Stackdriver to sort of like send a probe to all our services and check whether these are up and running, whether there's a downtime or stuff like that. We can monitor like that. So that's observability. And with all of these things, we can set up alerts as and when required. And then, if manual intervention is needed, we can go and do certain fixes, or like, or we can automate certain such things as well. Like, let's say, for example, if resource usage is high, automatically scale the system. You don't have to alert anyone, just scale the system automatically, add more VMs or stuff like that. So that's a quick intro to observability. And the monitoring tools for this one we can use, I already mentioned here. These are alternatives. So the ones in green are the ones we are going to use for this case study. So it's going to be Cystic Falcon for for runtime security scanning, and Zipkin for open telemetry, that is latency and tracing, Stackdriver for logs monitoring, monitoring and alerts. Okay, right. Then we are going to jump into deployment methods. Remember, I told you early in the slide deck that we are going to be using a rolling update deployment pattern, because the developers would be just doing patch fixes rather than breaking changes. They are going to be doing bug fixes, and the bug fixes needs to be immediately released rather than go with other routes. So let's look at what the deployment methods are and why we chose rolling update. So Highlander is is a very basic deployment method. What happens is that you have version 1 of your application, you just put version 2 directly, replace version 1 with version 2 directly, right? So what happens is, if there's a problem with your version 2, version 2 will be a bug fix, but even in a bug fix, the bug fix could be opening up more bugs, and the system might be problematic, or it might crash, right? In this scenario, if this is a faulty bug fix and you replace everything with v2, the system is down now, right? And you had to roll back to v1 manually. That's bad. Second one is canary deployment. So in canary deployment, what's going to happen is, you are just gonna update one instance to v2, and then you are gonna split the traffic like 30% to version 2, and then 60%, 66% to the other version 1. So this is okay, but now again, given this is an election system, and this is just the night of the election that this would be running, uh, you don't really have time to do traffic splitting and do all of these things. You need to, you're pushing a patch because there's a bug. The bug needs to be fixed, right? So there's no point of pushing this data to v1. So that's why canary deployment is not ideal for this particular case. But in most scenarios like Facebook, Google, etc., where you're developing a new feature and then you want to release a new feature, canary deployment is sort of like the very best approach. Then there's something called blue green. Blue green is, you would have version 1. While version 1 is there, you would deploy version 2 separately. And now version 1 and version 2 is both running in the system. And then you would just switch traffic from version 1 to version 2. And if something goes wrong in version 2, you would switch traffic back again to version 1 and make sure your users are not affected, right? That's what it happens. So blue green is mostly there when you do a major upgrade, like a complete rewrite of your entire software, and then you are pushing it to the users. So something like that, blue green would be ideal, because then the users will be using the old version or the old software, and then you push the new one, and then you forward the traffic, switch the traffic to the new one, and if everything goes on, then fine, it's good. But if something is wrong in your new version and things are acting very crazy and weird, you can always switch back to version 1, and users will not have a downtime, and the system will be functional. Finally, rolling update, which is what we selected for this election system, because at the end of the day it's a bug fix, and the bug fix needs to be rolled out immediately. But also, like if there's a problem with v2, the bug fix, the update should stop. It should remain at v1, and then we should be notified that there's a problem, right? So how rolling update would happen is, it would just out of the three, it would just update one, and it would make sure that v2 is running, and it's healthy and it's running properly. If it's running and healthy, only it's going to start updating the next one and the next one. So it's just an iterative thing, and it's automated. So that's sort of like our requirement for the election system. Okay. And right, so I have about 15 minutes more in this presentation. So the next thing is, we need to set up resiliency, and to do that we are using service meshes, right? The reason for jumping into service measures and not setting up resiliency within the application itself, the microservices itself, is because our microservices in this election system is not written in the same language. We are using Java, we are using Python, we are using Node.js, and there's a couple of Go codes, right? So it's very hard for us to do discovery, load balancing, resiliency, tracing, and metrics, and all of these things, because these languages are now different. The frameworks we are using are different. It's hard. So because of this, we can, and then integrating all of these things into these services is going to be a massive overhead. Rather than that, we can basically use a service mesh architecture where all the requests that are going out of these applications would be going through something called a sidecar proxy. Rather, in this scenario, service A is directly calling service B. But here what happens is when service A wants to talk to service B, it goes through the sidecar proxy, and sidecar proxy manages the connection. So with this, we can basically do a lot of things which I'll be talking a bit later. And with this, we can do tracing, we can look at observability, we can look at tracing, the latencies, and we can do a lot of these things via service mesh approach. So the features of service meshes, and I'll tell that the ones that are in green are the reason why the features we are using for the election system by using service meshes. The first one is observability. We need to look at how the latency of this software, these APIs are, what APIs are the slowest, and all of these things. Tracing, another thing. We need to trace a request. We need to see how things are working out. Another one is called mutual TLS security, like the communication between instance A and instance B. There's a protocol called MTLS. Using that, we can very easily encrypt the data here as well, so that no one in the middle can sort of like get the data or alter data or do anything, right? So that's called mutual TLS. So we can enable that very easily via service meshes. If there weren't any service mesh involved, implementing MTLS would be a bit hard. Like there's a lot of work you need to do. And then there are some advanced network traffic routing. There's a lot here, but we would be using circuit breaking here. So what circuit breaking would do is, like, let's say, for example, we are sending requests for a given microservice which has three replicas like this. And if one of these replicas is sort of like hot as in, it has a lot of load, and it's very slow. So what circuit breaking would do is, it would identify that this particular one is struggling, and it would just keep this out of the pool, and it would just start forwarding traffic to the other two, and then leave this out for a while for it to cool down. And once it's cooled down, it's rejoined back into the pool, and it just gives more resilience to our services, right? And finally, chaos engineering. I'll talk about chaos engineering in the next slide. So there are two service mesh tools. You can see the comparison. We are going with Google, and Google by default has Istio enabled. We can enable it Istio, so that would be our go-to. And basically, because we wanted circuit breaking only, the Istio is a better choice here, because Linkerd doesn't support circuit breaking at the moment. But if you just need MTLS, and if you just need tracing and observability, Linkerd would be a better choice. It depends on your requirements. Final step is chaos engineering. Now we have set up our environments, we have deployed our application, now everything is running, observability is there, alerts are there, all of it there, right? So now it's fun, right? But when shit goes bad, shit goes really bad, right? So you need to be ready for it. So that's where chaos engineering comes into place. So what happens is, before shit gets bad, we would try to break our system on purpose. We would try to load it with requests. We try to find out the weak spots, and we try to break it. We just run chaos, and then we see how our system reacts when we do this chaos. Like, remove the database, or make the database read only, like how our system reacts, what happens. So when we do this, it actually doesn't really cause problems, it reveals the problems that we have. Like, all right, so then we know, all right, so this happens, this is a problem, we need to fix it, sort of a thing. So that's what chaos engineering is. So we try to break our system on purpose, just to make sure and just to be more confident that our system is, working properly, and then we can go into production and to the election day in a very confident manner that, your system you have tested and it's working, right? That's called chaos engineering. There are a lot of tools to do chaos engineering. I have put top three. So for this one, because we are already using Istio, we can use Istio as the uh, chaos engineering tool. Maybe we can use Gremlin too, but yeah, Istio is my go-to to inject failure codes. Um, yeah, and that's basically it. Like, this is sort of the case study, like how if I were to implement the election system on Google Cloud, these are the tools that I would use, these are the processes that I would use, and these are the things that I would do. um, yeah, and like, and also just make sure that this is just a hypothetical, this is not the actual implementation that we did, just a hypothetical, just putting it out there again. um, and then finally, if you want to learn more about DevOps, my friend Arjad Zakaria is doing a podcast called DevOps with Zach. He talks a lot about these principles and real world case studies. He brings in a lot of people to discuss their experiences and etc. So have a listen to that, and you will understand more about DevOps. Right. So that's it. I hope this was interesting to you. Questions?
Okay, guys. If you have any questions, you can talk to our social media, and you guys can contact Nilesh Chand through social media, and you can hit your questions to Nilesh and Silkfast community. So it's to conclude the session, and thank you so much, Nilesh Chanandana, software architect at WSO2. Hope you enjoyed the session, and thank you everyone for participating for this session, and hope you to see in another session. So thank you, thank you everyone. Good night.